new chapter that is basically a theory of Martingale. So in this chapter we will consider two cases. One is discrete time martingale and another is continuous time martingale. Okay, so first I will take say 2-3 classes on discrete time martingale, and then you will see that continuous time martingale, all the results of discrete time martingale holds, or it can be extended to continuous time martingale. So continuous time martingale means basically you have seen the stochastic process xt. Whenever that capital T I consider, if it is a 0 to infinity, suppose, okay, or if it is a sequence, that means if T is equal to my natural number set, then it's a sequence, and that is called the discrete time martingale. Okay, so I will define what do you mean by the martingale and so on. So why this martingale theory is important, you will see later on. Okay, because even if it has a applications in finance and many other places, it has applications. Okay, so even you know strong law of large number and so on, using martingale theory or the martingale concept, one can consider a different proof which is really simple. And not only that, you will see in this chapter that you have that gambling systems, and then when to stop this game and so on. So there you will use the application of martingales and so on. Okay, so it has many important applications, and not only that, later on in particular for continuous time martingale, it has many applications in real life problem, because most of the real life problem you model it using kind of say stochastic differential equation or stochastic partial differential equations, and if you want to solve that part and so on, so there if you try to write down the solutions to that problem, that will come in terms of Ito integral form, and there the martingale theory or the properties of martingale comes into picture, and so the theory of martingale is really important. Okay, so first we will consider the discrete time martingale. So for that, I need to know what do you mean by the conditional expectation. Okay, so already you know the definitions of conditional expectations you have seen from your probability course. Okay, but here most of the cases I'll try to state the properties of conditional expectations, and few things actually I'll try to prove it. So what is your conditional expectation? What it says that suppose I have say random variable space omega f and p. The f is the filtration, p is your probability, and now x is given to you, which is say L1 of omega, means integrable. L1 of omega means basically that is expectation of mod x is finite. Okay, so this is expectation x is in L1 omega. This is the notation actually I am considering. So suppose you have another sigma algebra. This is a sigma algebra of omega such that my nu is a subset of f. Okay, so this is a subsigma algebra of the sigma algebra f. So what is the conditional expectation? So the conditional expectation of x given the sigma algebra nu is a new measurable random variable, so denoted by expectation over x given nu. This is the notations. Okay, so denoted by such that what is the property that if you consider any measurable set A from nu, so that is the notation A is from nu, then x dp, this should be same as integral over A x over x given nu dp. This holds for all A is in my nu. Okay, so then this random variable expectation over x given nu, which is the conditional expectation of x given the information nu. Okay, so you see that if my sigma algebra is trivial, means if my nu is trivial, so in that case, so maybe you can check it. Okay, so if you consider again the expectation of my conditional expectations, this gives me expectation over x. Okay, if you consider the expectation over x given nu, this is equal to expectation over x. Is it not? Because this holds, so if I take A is equal to my omega, is it not? So this is integral over my x dp, this is nothing but the expectation of x. Because A is in my nu is the sigma algebra of your omega, so omega, capital omega is an element of your omega. This holds for all A, so from the definitions, it is clear that expectation of x given nu is equal to expectation of S. And another thing is that if you consider the trivial sigma algebra, so check it yourself that if my nu is the trivial sigma algebra, so that means basically I have p and omega, then what I have, this is expectation of x is same as my expectation over x given nu. Okay, so this is same as expectation over x given expectation over x given nu. This is for the trivial sigma algebra, you can check it. So now I have defined the definitions of conditional expectation. So question is whether conditional expectation exists or not. Okay, so this I will try to prove it, because it involves little bit, you will see that nice information, because since you know some kind of say function analysis there, so you will see some kind of proof. So it basically what it gives you there, it is the least square approximations. Okay, so whether you can best think of. In particular, what I'm saying, so let x is a random variable belongs to L1 of omega, means it is an integrable random variable. Then for each sigma algebra, say nu, which is subset of F, expectation over x given nu by definition it exists, and not only that, it is unique. So this is a random variable. So whenever I am talking about the unique, that is means it is a almost sure sense. It is unique up to a new measurable set of probability 0. Is it not? Because this is a random variable. Okay, so whenever we say that okay, x is equal to y, p almost surely, that means I can throw the p zero measurable set where they may not be equal. So that is why they say that it is unique up to a new measurable set of probability 0. Okay. Okay, let us try to first do the proof of uniqueness. Okay, because I think in your probability course you know this theorem, but we have not done the proof. That is why here I try to give the nice proof for that. So now what I'm saying that now suppose I have two conditional expectations for that for the given x. So suppose I have y and y tilde, okay, both satisfy the definitions of or satisfy the criteria of conditional expectation of x given the sigma algebra nu. Okay, that means what I am saying that y and y tilde both are new measurable and it satisfies that integral information or integral equality. So what I have to show? I have to show that y is equal to y tilde new almost everywhere. Is it not? So for that, if I try to show that y minus y tilde greater than 0 or greater equal to epsilon, for epsilon any arbitrary, that is measure 0 set, and similarly if y tilde minus y, which is again greater equal to 0, that is of measure 0 set, then we are done. Is it not? So that means they are equal with probability almost surely. So for that, I am just considering, so given epsilon positive, I am considering this set epsilon, which is all those omega, where y omega minus y tilde of omega is greater equal to epsilon. So our aim is to show that probability of a epsilon is equal to 0. Okay. So now see y is in nu. Y tilde is also new measurable. Hence this a epsilon, this is basically is in nu. Is it not? So a epsilon is in nu. So nu is in sigma algebra. So epsilon is a event form there. Is it not? So now since a epsilon is nu, and then I can use my conditional expectation definitions of conditional expectation. So this implies I can write down that over a epsilon, this y minus y tilde over dp, this is actually 0. Is it not? Because if you look at there, here that integral x dp is equal to integral over a, this is my y dp, and this is again same as integral over a y tilde of dp, because suppose there exists 2. Is it not? We try to show the uniqueness. So from there, what I have here, that since my a epsilon is in my nu, I have a epsilon y minus dp is equal to 0. Okay. So now on the other hand, on this set a epsilon, that epsilon is less than equal to y minus y epsilon. So this implies 0 is less than equal to epsilon of p of a epsilon. Okay, and this part is less than equal to integral over a epsilon over y minus y tilde over dp. Is it not? But this one is actually equal to 0. I am having from here. So this implies that what? That probability of my a of epsilon is 0, because epsilon is positive. So p of a epsilon is equal to 0, and this holds for all epsilon is positive. Okay. So now I can again write down this is 0 less than equal to probability over all those omega where y minus y tilde, this is strictly greater than 0. So these things actually I can write down, this is probability over, I can take summation over n is equal to 1 to infinity, okay, a of 1 by n. Is it not? So I can choose epsilon is equal to 1 by n, and then you took that union. So that is why I have this part. So this is less than equal to by because this is infinite sums, I have summation over n is equal to 1 to infinity probability of a of 1 by n. Is it not? Just choosing epsilon is equal to 1 by n. And now p of a epsilon is equal to 0 for epsilon, hence this one is actually 0. So what you have, that this one is equal to 0, hence y minus y epsilon less than equal to 1. Okay. So this implies probability over all those omega y minus y tilde is less equal to 0, because this is the complement, this is actually 1. So this implies what? This implies, that means y is less than equal to y tilde almost surely, that is the meaning. So in the same way, just you can replace y, switch the y and y tilde. So similarly, we can show that y tilde is less than equal to y almost surely. So this gives the y is equal to y tilde almost surely. Okay. This gives the uniqueness. Let us prove the existence. So why I am doing this proof, existence proof, you will see that is very nice property. So in particular, first we will try to prove this existence of conditional expectation for L2 random variable. L2 random variable means basically, suppose my random variable x is in L2 of omega. Okay. So the case 1, x is in L2 of omega. Okay. So then already you know what is my L2 of omega. This is consist of all real valued random variable such that I can think of their norm. No, okay. So norm of x integral over omega y square dp whole to the power 1 by half is finite. This is already you have seen in your, I think, function analysis course, is it not? Since you have all done the function analysis course. So that L2 of omega, I am considering the norm of here, and not only that, I can define the inner product on this space. So basically, if you have say y1 and y2, it is in L2 of omega, I can define y1, y2 the inner product. Okay, or maybe I just put as a bracket. This is by definition integral of omega y1 y2 over dp. Okay, this is nothing but the expectation of y1 y2. Okay, this is the nothing but the y1 and y2. Okay, so now I am considering the space V, which is the L2 of omega 2 nu. That means it is again the square integrable martingale, but this is nu measurable. Okay. So V, which is L2 omega nu, means this is the space of all square integrable random variable which are nu measurable. So this one, whenever I have L2 omega, I am not writing as a f, that is just for the notations, because it is trivially for there. But since I am considering the measurability in a particular sigma algebra, that is why I am mentioning here. So V is my L2 of omega 2 nu, and where nu is my subset of or the subsigma algebra of F. Okay, subsigma algebra of F, mathematical F. So it say this V is a closed subspace of L2 omega. So this is a closed subspace of L2 of omega. So consequently, since it is a closed subspace, okay, in your functional analysis course you have seen that I can think of the projection. Okay, so I define the projection of x on V. That means you can think of, suppose this is your the space V and x is somewhere else. So what is the projection? Projection should be the smallest distance, no? Is it not? So I can define the projection, since it is a closed subspace of L2. So define the projection that Z, which is nothing but the projection of X on the closed subspace V. So then what you have seen that it satisfies the property that this has the distance which is the minimum distance. In particular, that means that expectation of z minus x minus z square, okay, this is the infimum of that is the minimum. So that means I can take, if you consider any w from my space V, and then if you consider the expectations of that square, okay, so that will be the minimum for all w is in my L2 of omega 2 nu. Okay, that is why that's the projection, which is it gives the shortest distance. And not only that, you have some kind of orthogonal properties, is it not? And second is that x minus z and then the w, they are orthogonal. That means the inner product is equal to 0 for all w is in my L2 of omega to omega nu, this space. So that means that is integral over omega x of w dp by definition of my inner product, and inner product you see that it is again the kind of the linearity is there. So this is nothing but that x z inner product minus zw inner product. So this is same as integral over omega z of w dp for all w belongs to my L2 omega 2 nu. Is it no? So now if I take, because in my definitions of conditional expectation what I have to show that integral over a x dp. So now if I think of w which is equal to characteristic function over a, so this one is nothing but then integral over a x of dp, is it not? But this should hold for all a from my sigma algebra nu. That is why I am considering. So let a belongs to nu, okay. Now consider w which is my characteristic function over a. So you see that since a is my new measurable, then w in my space V, okay, which is L2 omega 2 nu, because this is new measurable obviously because a is in nu, so this is new measurable, and then it is in L2. So w, if I consider these things, and then if you put in this orthogonality property, then what I have, okay, so this implies w is in my L2 omega 2 nu, and not only that, integral over a x dp, which is integral over a z of dp for all a is in my nu. So this implies by definition z is nothing but what? So z is nothing but the conditional expectation over x given nu, is it not, by definitions? And also it is unique, already we have proved it. So what we have seen from here, that the conditional expectation over x given nu, this is nothing but the projections, is it not? So which is that something that I am saying that the least square approximations with respect to that. This is the projection, the minimum distance here for condition is that my random variable x now is in L2. But in my theorem, what I am saying that if x is in integrable, then I can do these things, is it not? So that means I want to show it what happens if x is in L1. So case 2, that x is in L1 of omega. So then idea is basically we try to approximate our L2 function, okay. And for L2 function we know that it exists, and then we try to pass to the limit. That is the general idea, okay. So what I can write down, generally x can be written as x plus minus x of minus, you know that's x plus and x minus, this is maximum over 0 and x minus is minimum over 0 and x, okay. So and this both x plus and x minus are positive, and we know that this integral is basically linear and so on. So without loss of generality we can assume that x is non-negative, okay. So without loss of generality, we can assume that my x is non-negative, okay, and x is in L1 of my omega, okay. So now I have a non-negative integrable function. So what I can choose? I can choose, so we can choose xn sequence from L2 of omega such that my 0 less than equal to xn, which is increasing to x, okay. So now I am considering, say, Zn. So now xn is in my L2, and from my part 1 or the case 1, I know that conditional expectations of xn given my information nu exist. So Zn, I can think of this is expectation of xn given nu which exists by case 1. Is it not? So now my claim that Zn is positive and increasing. So this fact actually it comes from the general result, okay. So why I am considering that xn is in L2 of omega and so on? Because in your measure theory already you have seen, no, that if you have an integrable function, then we can always find it is a non-negative integrable function. So whatever we have done there, that okay, I can find a bounded sequence of fn such that my fn converges to f there, no, monotonically. So since it is bounded, it is automatically L2. That is why I wrote down that okay, we can choose xn is in L2 such that 0 is equal to xn, which increases to x. Okay. So my claim is this Zn, which is the conditional expectation of xn given nu, this is positive. That is actually you expect, no, because xn is positive greater equal to 0, non-negative. So you can expect that Zn should be also non-negative, and since xn is also increasing, it should be also increasing. So this result follows from the general fact. What I am saying that if you have a non-negative random variable, so general fact, so if u is a non-negative bounded random variable, then conditional expectation over u given nu greater equal to 0 almost surely. Okay. So how to prove this thing? So I read, let's say my y equal to expectation over u given nu. Okay. So what I have to show? That I have to show that y is greater equal to 0. So I am just considering the contrapositive argument. Now suppose, so if possible, let y is negative, okay, with probability greater than 0. Because what I have to show that probability of y negative, that is equal to 0, then we are done. But I am saying that suppose if possible, because probability should be non-negative. So that is why I am considering suppose it is a positive. Okay, probability of y is negative, the probability of that is positive. So then I am considering some set g such that y of omega which is greater than minus 1 by n, all those omega. Okay, so now this is in my nu, is it not? Because y is your new measurable because of these things, and then y of w less than minus 1 by n, this should be your new measurable. Okay, so now this has positive measure. So for some n, g of n has positive probability. Is it not? That is because probability of y less than 0, which has positive, that means for some n, okay, at least for some n, I have this quantity. Okay. So this implies that 0 is less than or equal to integral over g capital U of dp. This is same as my integral over g y over dp, because u is non-negative. Okay, u is non-negative, so 0 less than or equal to integral over g u of dp. That is actually we know from the integral things. And then this is same as this is integral over g u dp is equal to integral over g y dp, because y is nothing but the conditional expectations of u given nu, and g is my new measurable set. So this part, and now from this set g, if you look at, this should be less than minus 1 by n probability of g. Okay, and probability of g is positive, so this part is basically negative. Okay, so what we have, 0 less than or equal to this part is strictly negative, so it's a contradiction. And this contradiction, because we are considering, I mean, we said that okay, if possible, this will happen. Probability of y is negative, which has the positive probability. So this is not the case. That means this implies that probability of y less than 0 actually is equal to 0. Is it no? So this is probability of y equal to 0 is equal to 1. That is my y is greater equal to 0 almost surely. So from there actually what I have, that Zn, this is positive, greater equal to 0, non-negative, and increasing to Z. So now let Z, I can write down that lim sup over n of Zn, and then since each Zn is my new measurable, and then the lim sup of Z is new measurable, hence my Z is new measurable as Zn is new measurable. Okay, and what I know, that my Zn, which is increases to Z almost surely. Hence, by monotone convergence theorem, I hope you remember the monotone convergence theorem. What it says that, suppose I have a non-negative random variable, and when it increases to say xn, I have a non-negative random variable which converges to x increasingly. Okay, and also it is monotone, so monotonically increasing or decreasing. Suppose it is monotonically increasing to x almost surely, then I can interchange the integration and limit. Okay, that means integral over say omega Zn is equal to integral over Z. Okay, so we can interchange the limit and integral. That is the monotone convergence theory. So here what I have, integral over a Z over dp. This is limit n goes to infinity, integral over a my Zn dp, and this is same as limit n goes to infinity, integral over a xn dp. This is because my Zn, this is a conditional expectations of xn, so I have the same thing else, and this is nothing but integral over a x of dp, because my xn converges increasingly to x, and xn is non-negative, again you can use the monotone convergence theorem. So what I have then, integral over a over z dp, integral a over z dp, this is same as integral over a of x dp for all a is in my new measurable. Okay, so a is the event from new. So this implies by definitions that z, which is equal to conditional expectation over x given new. Okay, So this completes the proof of existence of conditional expectation. So what it says that if you have any integrable random variable, then for any sigma algebra nu, there exists a unique conditional expectations of x given nu such that they satisfy that conditions. Okay. So I am not going to going to prove the certain properties of conditional expectations. So you can check yourself. Already I think you have done it in your class. Okay. So some properties of conditional expectation. So first property is that if my random variable x is new measurable, then what happens? So this is first condition. So for any new measurable random variable x, okay, what I have that conditional expectations of x given nu is same as my x almost surely. Okay, you check yourself, then actually you will have this part, because since x is my new variable, by definition integral over x dp, this is same as my integral over x dp for all a. Is it not? Because x is new measurable, so it is trivially true. And second is like in your integration, see expectation is nothing but the integration, no? Integration over omega x of dp. So what we know that integral is linear. So here we'll see that conditional expectations is also linear. So in particular, what I have that if you have a x plus b over y, where x and y both are integrable and a b are any real number, so ax plus by are integrable, so then I can talk about the conditional expectation. Then what it says that if you this thing, then actually it is linearity holds, means a of expectation over x given nu plus b of expectation over y given nu. Okay, such that all these things make sense. That means my x and y should be integrable, so that actually it makes sense. Okay, you just check it, by definitions it will come, nothing else. You write down this left hand side, then actually it will come in terms of integration, and then you know the linearity from there, so it will automatically come. Three important properties that, so if x is new measurable, and x of y is integrable, then means I just look at the product things. So what it should be that since x is new measurable, you can take out x times expectation over y given nu. Okay, so that y is also integrable, so that this I can talk about the conditional expectation of y given nu. Okay, and the more, so sometimes actually we will also, you will see later on we will use this condition 3 more and more, means all these conditions we will use often. Another is called the tower property. So what it says that this tower property, it will be clear from, means if you pictorially you can think of what it says that, so if you first take the conditional on a bigger sigma algebra, and then if you consider the smaller sigma algebra, this is same as actually if you consider the conditional things on lower sigma algebra, because that is because of the projections and so on. Okay, so what I am saying is the following, that for W, or maybe another I put G, this is subset of nu, both are the sigma algebra. Okay, then that expectation over x given G, these things actually I can write down expectation over x given nu, you consider first that nu, this is the bigger sigma algebra, and then take conditional things with respect to your g. Okay, this is almost surely. And now this part, I can think of x given nu, this is trivially true. This is expectation over x given g, and then if consider conditional things with respect to nu also. This one is trivially true because of your measurability, because expectation over x given g, this is g measurable, is it not? And g is a subset of nu, hence x given g is nu measurable. Already you have seen that if your, so this thing is now nu measurable, and hence expectation over x given nu, this is same as my expectation over x, means that the random variable itself. Okay, so that is why actually we have it from 1. So from 1, this part is trivial, but the tower rule or the tower property, what it says that if you want to think of the conditional expectation of any random variable given some sigma algebra, we consider the conditional expectations with respect to bigger sigma algebra and take the conditional expectation of that with respect to the given sigma algebra. Okay, this is the tower property. And another means there are many, in particular all these convergence results like monotone convergence, bounded convergence, dominated convergence theorem, what you know for the expectations or for random variable. So this should be hold for the conditional expectations. Okay. So in particular, I have the monotonicity property. What it says that if x is less than equal to y almost surely, and if y is your integrable, then I can talk about, because if y is integrable, then x is also integrable. Okay, then what I have, okay, so mod maybe I can think of, then expectation over x given nu, so I can think of something like this. Suppose x less equal to y almost surely, and x and y both are integrable. So then expectation x given nu, this is less than or equal to expectation over x given nu almost surely. This is monotonicity property, and already we have seen automatically there. So that if my xn is greater or equal to 0 and xn monotonically converges to x with expectation over x is say finite, so that I can talk about the conditional expectation of x given nu, then expectation over xn given nu, this is increases to, means increasingly converges to expectation over x given nu. This is already we have seen it there, is it not? From the proof of existence of for L2ness. Okay. So now we know the Jensen's inequality, you know, Jensen's inequality for measurable space and so on. So same thing else actually we try to look at for conditional Jensen's inequality. That is, I put as a lemma. Why this Jensen's inequality is important? Later on, actually, you will see that using this Jensen's inequality, if I give you a say martingale, then I can produce a more sub-martingale. Okay, so I'll give the meaning. What do you mean by that, and so on. Okay, so let us consider first the conditional Jensen's inequality. So basically, what is Jensen's inequality? What it says that if you have a say, if you have a say measure space with total measure is equal to 1, then actually, and if you have a convex say functions, then if you look at the compositions of phi, then what it says that phi of integral over omega f, this is less than equal to integral over f of phi, phi compose f of d mu. Okay, so same thing else we try to write down here. Suppose phi is a convex function from R to R, convex, with expectation of p of x, this is finite. Why I need these things? Because as I say that, okay, I try to put these things inside. That means I need to define the conditional expectations of p of x. So for that, the condition is that it should be integrable. Okay, so I have such kind of p, then, and also x is your integrable. Then what it says that we first consider the conditional expectation of x given any, say, given sigma algebra, and then you apply p. This is less than equal to, you consider that px, which is again a random variable, and by these conditions it is integrable, hence I can talk about the conditional expectation. So this is less than equal to conditional expectation of px given nu almost surely. Okay, so the proof is simple, but it basically somehow characterizes how the convex functions look like. Okay, because if you have any convex functions, then what I can write down, that I can think of that, okay, look at any linear functions, and also h, where say h is less than equal to p, and then you took the maximum of that part, something like that, no? For square function, I know that x goes to x square is a convex function. That means you consider, no, at any point you consider any linear functions which is below my p, okay, and then take that maximum. So then actually p of x would be that part. So in particular, what I am saying, that since my p is convex, so you can expect my px, which is maximum over h is less than equal to p, h is linear. So I am considering this is the linear, in this case it is the line. Okay, so suppose at that point, or you can think of many places here, there, of my h of x. Okay, this is the characterizations of my convex functions from R to R. So now let h of x is equal to, say, ax plus b. Is it not? These are the only linear functions on R, no? Linear functions, x plus b form. So which lie below phi. Where phi is my convex. So then what I can have, expectation of phi of x given nu. This is less than or equal to expectation over ax plus b given nu. Is it not? Because my phi of x is less than equal to h of x. So phi x is bigger, and that is why I use this monotonicity property. This is greater equal to, and then expectations I have phi x plus b, and then it is linear. So this is a times expectation over x given nu plus b. Is it not? So now this is nothing but what? A of these things I can put as a variable. So that's means this is nothing but my h of expectation over x given nu. Is it not? So this implies, so what I have, expectation of phi of x given nu, this is greater equal to h of this part. So now if you consider for any linearity phi, so this implies what I am saying, that then the maximum of h of expectation over x given nu, look at my h is less than equal to any phi and h is linear, this should be less than equal to my phi expectation of phi of x given nu. Is it not? This is the part I have. So this implies then by definitions of phi, so this is nothing but my phi of expectation over x given nu, this is less than equal to expectation of px given nu almost surely. Okay, because all these things holds for almost surely, and then this is almost surely. So this is the Jensen's inequality. What it says that if you have a convex function and so on, then I have this part. Okay, So from here it's a simple thing is that if you consider my nu, so maybe remark, if I consider nu is equal to my trivial sigma algebra, nu is equal to phi and omega, and take my phi of x is equal to say x square. So then the Jensen's inequality says that, okay, for any square integrable, so then for any square integrable random variable say x, we have from Jensen's inequality, from conditional Jensen's inequality, what we have that this is expectation over x, because of the trivial things. What do we know that expectation over x given nu is same as my x, no? So in that case what I have, sorry, expectation of x, so phi is square, so expectation of x whole square, this is less than equal to expectation over x square. Already you have seen it, no? Not only that, what you have seen, that is called the Hölder inequality. So xy, okay, expectation of xy, this is less than equal to expectation over say x to the power p whole to the power 1 by p, expect to the power x to the power y to the power q whole to the power 1 by q, where 1 by p plus 1 by q is equal to 1. Is it not? So for the functions, actually you have seen it in your functional analysis course. Is it not? But this is exactly same, no? Nothing else here. This is L1 space, L2 space, and you can write down there. Okay. So now with this definitions and properties of conditional expectations in hand, we will define so-called the discrete martingale. Okay. Before defining the discrete time martingale, let us recall again. So I am saying that Fn, this is a filtration. What do you mean? That Fn is increasing family of sigma algebra, no? Is it not? And we define my f of infinity, which is union over n of Fn. So this may not be sigma algebra. Already we know that, no, that the union of a sigma algebra may not be a sigma algebra. So now we consider the sigma of this thing. So this is a subset of is equal to f. Okay, so f of infinity is a sigma algebra which is given in this form. Okay, so what this Fn basically, already you have seen that Fn is nothing but the natural filtration of some process which gives you the information about that process at time n. Is it not? Okay, so let us consider one motivations to define the martingale. So now suppose y1, y2 and so on, they are IID, independent random variable, okay, with expectation of yi is equal to 0. Now I am defining S of n, which is summation over I is equal to 1 to n of yi. So you can think of Sn is equal to 0. So now the question, so what is our best guess? S of n plus k given the values of S1, S2 up to S of n. Okay, so we want to know what is the best guess of S of n plus k. That means basically all the informations up to n plus k is given to you. What can you say about the expected fortune of Sn plus k or the future? So for these things, let us observe expectation of S of n plus k given S1, S2 and so on. So as I said that you can put S0 is equal to 0. So then what is this? This part actually I can write down, this is expectation over S of n plus k. This is summation of I is equal to 1 to n plus 1 to n plus k. So this is summation over, or maybe I can put as a S of n given S1, S2 up to S of n plus conditional expectation over summation over I is equal to n plus 1 to n plus k of yi given then the sigma algebra S1, S2 and S of n. Okay, so later on actually we write down that f of n, which is sigma algebra generated by Sns, S1, S2, S of n. This is exactly same thing else. Okay, so now what I know, this S of n is measurable with respect to the sigma generated by S1, S2, S of n. Hence this is nothing but my S of n almost surely, and then plus now S1, S2, Sn, I have these summations and each are independent. So that means I can take, so these things is independent of this sigma algebra generated by S1, S2, S of n. So that means what I know from the property of conditional expectation, that expectation of x given nu, if x is independent of nu, then this is nothing but the expectation of x. So this is expectation of summation over I is equal to 1 to n plus 1 to n plus k of yi. And now this is a finite sum, so you can take inside the expectation, and expectation of each yi is equal to 0. Hence this is nothing but my Sn almost surely. So what it says, that the best estimate of the future value of Sn plus k, this is the conditional expectation given the history up to time n. That means basically the sigma algebra generated by sigma 1, S1, S2 up to S of n is just S of n. So you can interpret this yi, this is as the payoff of a fair games of at time I. Okay, and your Sn, this is the total winning at time n. So now this above calculation, what it says, that any time one's future expected winning given the history of the winning up to time n or up to time date is just the amount, the current amount of money. Okay, that is basically S of n is the current amount of money. So expected of the future winning given the information, this is the current amount of money. These things, this idea, if you try to formulate as a formal definitions, that I define as a martingale. What it says, that a process, so x, so maybe a vector or whatever xn such that n greater equal to 0, okay, is called a martingale relative to a filtration, say f of n, if the following holds. First condition is that x is adapted. What means that is, for each n, fn is fn adapted or measurable. Okay, for every n. And second is that we have seen from this motivations, that I need to think of the conditional expectations. And for conditional expectations, what I need, that it should be L1, no? That means expectation of xn, this is finite for every n. Okay, we are not saying that it is uniformly L1. Uniformly N1 means actually supreme over that part. This constant may depend on n, but for each n, as long as your n is fixed, this should be finite. Okay. And third thing, whatever we have seen from there, that conditional expectation over xn plus 1 given f of n, this should be xn almost surely. Okay, this is called the martingale. And there is also concept called the super martingale or the sub martingale. So for that case, so super martingale, so in that case actually what I say, that exactly same condition 1 and 2 holds, 3 should replace by this form, that x of n plus 1 given f of n, this is less than equal to x of n, super martingale almost surely. And we say that sub martingale, so again 1 and 2 hold, and 3 is replaced by this thing. This is greater equal to xn almost surely. Okay. So again, a stochastic process satisfy this condition 1 and 2 such that this happens, then actually you can say that it is a martingale, sub martingale, or so on. Okay, let us consider one example whether we can have martingale or not, and so on. Okay. Okay. So one example. So suppose I have my y1, y2, they are IID, okay, with mean 0. And variance sigma square. Now I define xn, which is summation over k is equal to 1 to n yk, that whole square minus n times sigma square. Okay. So then my claim is this xn is a martingale with respect to the filtration fn, which is sigma generated by y1, y2 up to y of n. Okay. So xn is a fn martingale where fn is in this form. Okay, let us check it whether it is a martingale or not. So first of all, whether each xn it is integrable. Okay, xn is adapted because each fi is yi is fi adapted, because that is why the sigma is generated by yn up to y of n, and hence my xn is f of n adapted, because this is constant. Constant means basically it is not random, hence it is adapted to that all the filtrations, and hence xn is fn adapted. Okay, second is the integrability conditions. To check that expectations of xn, this is less than or equal to, now yks are independent, and then what I have from here, actually I can write down this is y1 plus y2 plus and then whole square, this is equal to n times of y1 square plus y2 square and so on, and yi or iid with the expression y is equal to 0. So what you have, from here you have n of sigma square and then plus n of sigma square. So at most I have n of 2 sigma square. Is it not? So for every n, expectation of xn it is finite. So this implies expectation over xn is finite for every n. Okay, so next I have to check that expectation of x of n plus 1 given f of n. So f of n means the sigma algebra generated by y1, y2 up to y of n. So what these things actually I can write down? This part I can write down that expectation of x of n plus 1. So I can have y over n plus 1 plus summation over k is equal to 1 to n of yk, this whole square, is it not? Minus n plus 1 times sigma square given f of n. This part I can write down. Just I write down x of n plus 1 is what is the meaning. So now this is square, I can explain it. So this is yn plus 1 square plus 2 over yn plus 1 summation over k is equal to 1 to n of yk, and then plus summation over k is equal to 1 to n of yk whole square. Okay, given f of n and minus n plus 1 times sigma square, because independent of this is a deterministic, so I can take out. Okay, so now these things what I can have, this is expectation of, again it is linear, this is y over n plus 1 square given f of n, now plus. So now these things k is equal to 1 to n y of k, okay, these all are fn measurable, and so now I can take out summation over k is equal to 1 to n of yk expectation over yn plus 1 given f of n, and then plus again this one is measurable. So then what I know, again these are the fn measurable, so I have this is nothing but that summation over k is equal to 1 to n yk, that square, minus n plus 1 of sigma square. So now this is, what is this part mine? I can write down expectation. See, y of n plus 1, they are IID, and fn is the sigma generated by y1 or 2 up to y of n. Hence, this is nothing but the expectation of y1. Okay, and similarly we have from here. So this is nothing but, because yn plus 1 that is independent of fn. So yn plus 1 is independent of f of n. So this implies what I have, expectation over x of n plus 1 given f of n. This I have now. This is expectation over yn plus 1 square plus 2 summation over k is equal to 1 to n yk expectation over yn plus 1, and then plus. So now from here I write down this is x of n is summation over k equal to 1 to n yk square minus n sigma square, and hence minus sigma square. So now this one is equal to expectation of yn square is exactly variance, because each y here IID with mean 0. So this is sigma square, and here actually this is 0. This one is sigma square. So this sigma square got cancelled out. So what you have basically, this is xn almost surely. So this implies my xn is a martingale. Okay. Okay. So let us consider one more example that is really important example. We will see later on also. That is called the Dupes Martingale. Okay. So what it says that suppose my Fn, it is a given filtration, and my some zeta, which is my L1 omega, that means integrable function, it is given to you. I am defining my Mn, which is the expectation over zeta given f of n. I can talk about, no, because for each n, Fn is a sigma algebra and zeta is in my L1 and the conditional expectation exists, we know. So I can define my M of n. So my claim, then M is a martingale. Okay, with respect to this filtrations Fn. So why this is so? If you look at, so one thing you observe that M is Mn is Fn measurable, that is by definitions of conditional expectation. So Mn is Fn measurable, basically by definitions of conditional expectation. Okay. Secondly, what I want to consider? We want to consider that whether this is integrable or not. So expectation of mod Mn, is it not? This is nothing but the expectation of mod of expectation over zeta given Fn, is it not? So now this f of x is equal to mod of x. This is convex function, is it not? And hence you can use the Jensen's inequality for conditional expectations. So this is less than equal to this part. I can have expectation over mod of zeta given f of n, is it not? And then take expectation. So this is a first you let the inequality and then take the expectation. So because under expectation actually it maintains the inequality. And now what I have? So mod zeta I have, and then expectation of expectation. So this is trivially expectation over mod zeta, and this is finite because it is given to you zeta is my L1, is it not? Zeta is in L1. Hence this implies expectation over Mn, this is finite for every n. So not only that it is uniformly integrable, later on actually we will see, but here actually that it is suprema over n expectation of Mn, mod of Mn, that is finite. That means it is uniformly bounded in L1. It is bounded in L1. Okay. Okay. So now we need to check that whether it is martingale or not. So for that, what I have to check it, expectation over M of n plus 1 given f of n. So this part is nothing but what? This is expectation over M of n. I can write down what? M of n by definition, this is expectation over zeta given f of n plus 1, no? And then take conditional to f of n. So now f of n plus 1, f of n is the filtration, so it is increasing. F of n plus 1 is a bigger filtration corresponding to Fn. So by tower rule, what I have, this is same as expectation over zeta given f of n. Okay, so this is by tower rule, tower property. Okay, and this is by definition, this is nothing but my Mn. So this implies my Mn is a martingale. Okay. So later on we will show that this Mn, this converges to M infinity, and this is nothing but expectation over zeta given f of infinity almost surely. Later on actually we will check this result. Okay. in the next part of these things you will check this result. So that means this is the Mn, which is the best predictor of zeta given the information available at up to time t, and M infinity, which is the best predictor of zeta we can ever make. Is it not? Because M infinity, because these things, this is the best predictor. That is actually we have seen it using this L2ness and so on, that B space actually we are considering. Okay. So this martingale is called the Dupes Martingale. This martingale, Mn, I have constructed, that is called the Dupes Martingale. Okay. Okay. So I will make one more, that is called the theorem. Actually I try to put it. What it says, that suppose my xn is a martingale, okay, and my phi, this is a convex function with expectation of phi over xn is finite. Then what can you about my phi of xn? Is a submartingale. So what I am saying, that for a given martingale I can always construct a submartingale. So you can construct many submartingale. So this is given by this theorem. This is my part 1. And part 2, that if xn is a submartingale and now phi is increasing, convex functions with that same property, then my phi of xn is a submartingale. Okay, so even from the submartingale we can construct many submartingale using this theorem. Let us look at the proof. Proof is really simple, where you will use the conditional Jensen's inequality. Okay, so what I have to show? I have to show maybe for the first cases. Phi of xn is a submartingale. That means what I have to show, that I have to show that my phi of xn plus 1 given fn, that is greater than or equal to phi of xn. No, then actually it is a submartingale property, because that is smaller. No, so look at, so now expectation of phi over xn plus 1 given f of n. This part actually I want to know. So now these things, now phi is convex. Phi is convex. So my Jensen's inequality for conditional expectation, what is say there? This is phi of conditional expectation over xn plus 1 given f of n. Is it not? This is by Jensen's. So now xn is a martingale. This is same as my xn is a martingale. So this is same as my x of n. Almost surely. So that means what I have having phi of x plus given f of n. This is greater equal to phi of xn. So this implies phi of xn is a submartingale. Is it not? So for the second part, again I can consider the same thing else, but you need to, here actually I am not considering these are the same xn, but there what I have to prove, I have to consider that phi of xn plus 1, this is greater equal to x of n, and now if you apply phi, that means you need the increasingness, is it not? Because expectation of x of n plus 1 given fn, this is greater or equal to x of n almost surely, because it is a submartingale, and hence if we apply phi, then this is phi of these things is greater or equal to phi of xn, because phi is my increasing. And now use the Jensen's inequality from there, so you have this part. So for the submartingale case, if phi is my increasing convex functions, then we have this result. Okay, so we will just complete this proof. It's nothing. Let us consider one example. What I am saying, that if my xn is a martingale, then what can about my xn to the power p? This is a submartingale. Is it not? So now suppose my xn is a submartingale, and hence it means if it is a martingale, then it is also a submartingale, no? Because martingale case, if it is both martingale and submartingale and supermartingale, then also it is a submartingale. So xn is a submartingale. Then I consider the function that phi of x is equal to, say, x minus a plus for anything, say. Now see that this phi is convex, so phi is convex and increasing. Thus xn minus a plus is a submartingale. Okay, so I'll stop today, and then we'll talk about next things. Even later on, actually, we'll talk about the convergence, when the martingale convergence, and where the convergence is almost surely, or in L1 or in LP. There are many convergence, no? Because since it is a random variable, so there are various kind of convergence modes, no? Various modes of convergence. Convergence in probability, convergence in almost surely, convergence in LP, and so on. So we'll talk about all these things and then certain applications for that. Okay.